This is Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we are going to discuss about the engineering materials. So, we have different types of engineering materials depending upon the applications. So, depending upon the applications, we have to select what type of material we have to select to the required application. As well as depending upon the properties, mechanical properties, we will differentiate the type of material and we can apply to the corresponding application. Now coming to the first material, we have the cast iron. So again the cast iron, how the cast iron is being formed means, so based upon the iron carbide diagram, we are getting this cast iron and different types of alloys from the iron carbide diagram. So that's why the study of iron carbide diagram is very, very important in order to identify what type of alloys or what type of materials are we are getting depending upon the composition as well as the temperature. Now, if you see the cast iron, generally the cast iron varies in the range of 2.14 weight percentage of carbon. So, above 2.14 weight percentage of carbon in the iron carbon diagram, we can identify the cast iron. So, cast iron are a class of ferrous alloys. So, these cast iron are class of ferrous alloys which are identified above the 2.14 percentage in the iron carbide diagram. So, what is happening? Most of the iron cast irons contains between 3.0 to 4.5 percentage of carbon. So, generally the cast irons are being available at this 3.0 and 4.5 weight percentage of carbon. So, at this point we can identify the cast irons and other alloy elements. Now, if you re-examine the iron carbide diagram, so what is happening here? In this iron carbide diagram, if the composition ranges becomes completely liquid in nature, at what temperature we are getting? At 1150 degrees centigrade and 1300 degrees centigrade. So, where is 1150 degrees centigrade? So, we are approximately getting at this junction. So, this is about 1150 degrees centigrade and 1300 degrees centigrade. At this point. So at this point, we are getting the composition range completely in the liquid form. So that is what we have to identify, and this is considerably lower than for the steels. So generally, any type of alloy or any type of material can be identified with the help of the iron carbide diagram based upon the composition. Based upon the composition, these alloys are being classified. Now, because of that liquidity nature of the cast iron, what is happening? The melting point and melting of this cast iron is very, very easy and it is open, free for casting. So, in order to do any casting process, so most of the materials are being used as a cast irons. Okay, so for castings, we are using the cast irons. Why? Because it is having the good melting temperature. So, that's why, and in most of the fabrications, we are using this cast irons as the casting process, and because of the cast irons are very, very brittle in nature, most of the castings are being conducted with help of these cast irons in the fabrication techniques. So again, this Fe3C, the cementite, is a metastable compound. That means depending upon the temperature, this is varying, the cementite is varying, so one form to another form. So that is called the metastable. So it depends upon the temperature. So variation with the temperature, this cementite is being transforming from one phase to another phase, that is from liquid to solid. So that's why if you see this cementite or the carbide, how it is being transforming? It is transforming into 3 times of the ferrite plus the graphite. So it is being transforming. It is decomposing with respect to the temperature. So that is one of the good thing where you can do the casting process very, very easily. Now, if you see the iron carbide diagram, so what is happening? Till now, we have seen up to 6.70 weight percentage of carbon. That means at that junction, we are getting the cementite. So if you extend that to 100%, we are getting graphite. So this is what we can observe. So in the previous sessions, we have discussed about at this point only, that is 6.70% weight percentage of carbon we have discussed. That is, we are getting the carbon into carbide, iron into carbide. But beyond that 6.70, if you go further up to 100% weight of carbon, we are getting the pure percentage of the graphite in this case. So you can identify the graphite here, and also at this point, liquid plus graphite, you can identify alpha plus graphite and gamma plus graphite. So below the 6.70 weight percentage, we are getting only the cementite products. But beyond the 6.70, till now we have not discussed about this graphite. So if you cross that 6.70 weight percentage, we can get the graphite weight percentage here. So here the figure is extending up to 100 weight percentage of carbon. So if you extend up to 100 weight percentage, we are getting the graphite in this, and the carbon rich phase we are getting instead of the cementite at 6.7 weight percentage of carbon. Now, slowly if you change the composition, what is happening here? You are getting the grey cast iron. So what are the cast irons are there? Generally these cast irons are, we are getting above the 2.41 weight percentage of carbon. Now if you still further try to identify the composition for the grey cast iron, what is happening? The carbon and silicon contents of the grey cast iron vary between 2.5 and 4.0 weight percentage and 1.0 to 3 weight percentage respectively. So like this, depending upon the compositions, your alloys are being varying. So that's why the compositions are very, very important. So in previous sessions, we have discussed about most of the compositions, how to identify the composition at any given point with respect to the temperature as well as the composition axis. So that's why if you know the composition, then it is very easy for us to identify what type of alloy is there, what is the microstructure of that element at some particular point. So in this case also, the grey cast iron are in the range of 2.5 and 4.0 weight percentage. Similarly, if you want to find out the silica, it varies from 1 to 3.0 weight percentage of carbon. So like that, you have to identify depending upon the percentage compositions of the carbon in the iron carbide diagram. So most of these cast irons, the graphite exists in the form of a flakes. So wherever the grey cast iron is there, so these graphites are existing in the form of a flakes. So like that, again, seeing that structure of the material, you can easily identify what type of material it is, whether it is a grey cast iron or white cast iron or a cast iron, normal cast iron. Like that, you have to identify depending upon the microstructure arrangement. So in the previous sessions, we have discussed about how there is a development in the microstructure when we are trying to cool the system. So when we are trying to cool the system, what is happening? The austenite is converting into pearlite, and that pearlite is having again some alternate layers of ferrite and cementite. So these are the combinations like that we can identify. So by seeing the microstructure, we can easily identify what type of material it is. Now in this case, the graphite is existing in the grey cast iron. So these graphites are arranged like a flakes. So you can see in this figure, the black regions. These are the graphites which are like flakes arrangement. So normal like similar to the cornflakes. So that's why it is named as a flake types of things, graphite flakes. So which are normally surrounded by again alpha ferrite or the pearlite matrix. So okay, so pearlite matrix is nothing but again you have the alpha zone. So what are the graphite flakes are there? These graphite flakes are surrounded by the alpha or the ferrite matrix. So because of these graphite flakes, what is happening? A fractured surface takes place on the grey appearance, hence it is named as a grey cast iron. So what is why the name the grey cast iron came into picture means, since these graphite flakes are looks like a fractured surface on the material. This is not. You can see it is looking like a fractured surface. So which is taking as a grey appearance, which is appearing for us to in the form of a grey color. That's why the name is given as a grey cast iron. So what are the composition which is in between 2.5 and 4%, we can get the carbon, as well as the silicon varies from 1 to 3 weight percentage of carbon. Now, whatever the graphite is there inside these materials, so these graphite is in the form of a flake, just like a similar to the cornflakes. And these flakes looks like in the structure like a fractured area. So the dark zone, what are the dark zone you are seeing in this picture? So these look like some fractured surface which takes place, and it appears like in a gray color. That's why the name is given as a gray cast iron for this material. So coming to that microstructure, next we will see what are the mechanical properties. So for each and every material, it is having its own microstructure as well as the mechanical properties. So depending upon the properties, we can justify or we can take that material and utilize to the required application. So this gray cast iron is now having comparatively very weak and brittle in tensile. So when any tensile force is applied on the body, on the gray cast iron, what's happening? It is having very less weak and brittle in nature when it comes to tensile. And of course, it is having its own microstructure, of course. And the tips of the graphite flakes, what are the graphite flakes we have seen in the previous slide? The tips of these graphite flakes are very sharp and pointed. Okay, and you have several points at stress concentrations. And of course, when you apply the compressive load on this gray cast iron, what is happening? Strength and ductility are very high. So for the same material, if you apply two type of different forces, when you are applying a tensile force, what is happening here? It is getting less in brittle, and when you apply a compressive force, it is having a much higher value of ductility as well as the strength. So these are the things you have to remember when you take any material to the required application. So before selecting the material, you have to know the applications, the properties as well as the microstructure, so that you can easily utilize the required material to the corresponding application. Now, most of the manufacturing materials, okay. So what is happening here during any manufacturing process? So during this process, the machine has some vibrations. It is having self vibrations during the working process. So these vibrations can be controlled if you have a strong base material. Now this strong base material, if we are preparing with a gray cast iron, then it is very useful to control the vibrations involved during the working operation. So that's why most of the machinery, when you compare with the steels have a lot of vibrations during the working process. Now the same steel, if you replace the base with the gray cast iron, you can control the vibrations. Now if you see in this figure, it is a comparison between the vibrations of steel and the gray cast iron. So this A, that is the blue color, represents for the steel, and this orange color represents for the gray cast iron. Gray iron. Now for the same machine with same RPM, if you're working, so what is happening? The steel has a lot of vibrations. So you can see all these damping forces. You have lot of vibrations involved. Now if the same machine is replaced with the gray iron, you can control the vibrations. So almost your 70% you're controlling by using this gray iron. So like that, depending upon the application, you have to select your material. So how to again select material? You have to know the properties. So how can you know the properties? Once you know the microstructure. So each and everything is interrelated to each other. Okay, the microstructure, the properties, applications, everything is interrelated. That's why one need to know a proper microstructure and the mechanical properties to identify the material to the required application. So in this case also, what is happening? When you compare any machine which is working with a steel material, it has a lot of damping thing or having a lot of vibrations during the working process. Now the same thing, if you replace with the gray iron, you can control the vibrations. So that is one of the good example when you see with the gray iron. Now coming to the white iron, this is another type of cast irons. So first one we have seen as a gray, Now this is the white iron. So depending upon the texture, depending upon the microstructure, depending upon the arrangement of all these ferrite or pearlite materials, so you have to identify you can easily identify the what type of material it is. Now for this, what is happening here? For low silica cast irons and rapid cooling rates, most of the carbon exists as a cementite instead of graphite. So during the cooling process, what is happening? Most of the carbon which is existing in that iron carbide is looks like a graphite instead of this cementite. So as indicated in this figure, you can see the surface of this alloys has appearance of in white in nature. So you can see some white patches here. Okay, because of these white patches, the material or the alloy or the what are the material you're seeing here, it is named as a white iron. So like that in the previous gray cast iron, that is appearing in the form of in the color of a gray. That's why it is called as a gray iron. Similarly, in this case also, the appearance, what are the patches, white patches we are seeing. So all these appearing in the form of white color. That's why it is named as a white iron. So like this, you have to identify or you have to differentiate by seeing the microstructure what type of material it is. The light cementite regions are surrounded by a pearlite. Again, what are the white region are there? These are again surrounded by the pearlite. So what are the dark region you are seeing? That is the pearlite. And the white patches you are seeing, it is white iron. So like that, you have to identify what type of composition you are having for the different types of irons. And these thick sections, whatever thick sections we are seeing, have only a surface layer of white iron. That's why when you are cooling the process, when you do the cooling process, the gray iron forms at interior regions. So interior, we can identify again the gray regions. And when you do rapid cooling of the material, and because of that rapid cooling, what is happening? Because of the rapid cooling, consequence of a large amount of cementite phase you can observe in the material. So like that, depending upon the type of cooling, whether you're doing a fast cooling or slow cooling, this appearance of the material will change, whether it looks like a white or gray. Like that, if you have different types of textures you can see in this. And again, white iron is very limited in applications, and because of its very hard and wear resistance to surface, and without a high degree of ductility, for example, most of the roller type of applications. So when you want to reduce the dimensions or reduce the thickness of any material, we have to do the rolling process, is it not? So in that rolling process, you can use these white irons to do the working process. So it is having very limited applications when you compare with the gray cast iron. And the other type of cast iron is the malleable cast iron, and this is generally we can get at intermediary in the production between the gray as well as the white cast iron. So you can see the patches, dark patches. These are called the pearlites. Okay, and the dark graphite rosettes, and these are the again alpha particles. So like that, you have three different structures for the three different materials. You have white, gray as well as malleable. So depending upon the structure, depending upon the applications, you have to identify what type of material it is. Now if you see the complete properties of individual material, so what is happening here? You have gray iron, ductile iron, malleable iron and graphite iron. So again, in these you have different sections or different grades. So coming to the gray cast iron, you have again SAE G 1800, SAE G 2500, SAE G 4000. So like that, you have subsections, subgrades. So why these grades means it again, these grades have different compositions of carbon. So if you vary the composition of carbon, what is happening? The applications again differs. the property differs. So depending upon the composition, these grades are being given to each element. So here if you see SAE G1800, you have some unique number F10004. Now if you see the composition of carbon and silica, you have 3.40 and 3.7 percentage of carbon and 2.55 of silica and 0.2 of magnesium. So like that you have different compositions. So depending upon the composition, so what type of structure you can see in this SAE G1800 means ferrite per perlite. So both combinations. Again, if you go with the mechanical properties, the tensile strength will be 124 megapascals. And if you see the application, so where you can use this SAE G1800 means it can be used in miscellaneous soft iron castings in which strength is not the primary consideration. So where the strength is not primary in considerations, then you can go with this SAE G1800. So like that, again, one more thing you have SAE G2500. Again, if you see the compositions, it again differs with respect to the previous one. So what is the range of carbon here? 3.2 to 3.5% of carbon, 2.20 of silica, and 0.8 of magnesium, like that. And if you see the matrix, you have the same, almost it looks like a ferrite and perlite. And the tensile strength here, it is increasing, 173. In the previous case, the strength is not that much considered. That's why you are going with that 1800. But now, here the tensile strength is 173 megapascal. So what is happening? Where can you use this grade of gray cast iron means? It can be used in small cylinders, cylinder heads, piston clutch plates, transmission cases, like that. These are some of the applications. Like that, depending upon the grade of the material, depending upon the composition of the material, depending upon the properties of the material, these applications are being classified. So like that, you have to identify what type of material is useful to the required applications. So like that, you have different malleable cast iron, compacted cast iron. So if you go with this malleable, so again you have two types of grades here, 1 and 2 in malleable. So you have 32510 and 45006. And again, this is given as some unique numbers. Now, what is the composition of this malleable at 32510? Grade means 2.3 to 2.7 of carbon and 1 to 1.75 of silica and less than 0.55 of magnesium. Like that, you have difference in compositions. So with these difference in compositions, if you see the matrix of that, you can see only the ferrite. Only the ferrite is available in the malleable at 32510. And coming to the tensile strength, you have a larger value of 345 when you compare with the gray cast iron. You are having good value of 345, as well as the yield strength is 224 megapascals. Now, if you see the applications, general engineering services at normal and elevated temperatures. So you can use at high temperatures, at elevated temperatures, and also the general engineering services, you can use this malleable cast irons. So like that, each material has its own applications, its own properties. So all these things you have to know to identify what type of material you have to select to your application. Those are about the ferrous alloys. Now coming to non-ferrous alloys. So what are the non-ferrous alloys here? Steel and other ferrous alloys are consumed in exceeding large quantities because they have a wide range of the mechanical properties. So generally what is happening? Steels and other ferrous alloys are being consumed. Why? Because these are having a good mechanical properties. So because of these wide variety of mechanical properties, most of the materials, most of the machinery are being consumed with this, and they are manufacturing with these steels and ferrous alloys. And these are again fabricated because of its very, very economic in nature. So that's why these ferrous and these steels are being adopted to do the manufacturing process. But again, these are having some drawbacks. So for every material, they have advantages as well as disadvantages. So coming to the disadvantages. So what are the disadvantages or the drawbacks for the ferrous and steels means? So these are very distinct limitations. So what are those? First one is the relatively high density. So because of the high density, what is the weight is increasing here? So because of the high density packed of the metal, the weight is increasing, and comparatively low electrical conductivity. So electrical conductivity is very, very less. So if the electrical conductivity is very, very less, then the life of the system or the life of the metal will get damaged. It get reduced. So the thermal conductivity should always be higher when you compare with any other material. And the other one is inherent susceptibility to corrosion to some common environmental. So when this ferrous and steel material is exposed to some environmental conditions, that is, it is exposed to some atmospheric air or water or some heat. So what is happening? It is getting some corrosion. So these are all some of the limitations for this ferrous and steel materials. Though it is having a wide variety of mechanical properties, but it is having some limitations like corrosions, thermal conductivity, less thermal conductivity, and very high dense materials. So all these some of the drawbacks. So that's why in order to avoid those drawbacks, we are going with the non-ferrous alloys. So thus for many applications, it is advantageous or even necessary to use other alloys that have more suitable property combinations. So that's why in order to replace those drawbacks, what we are trying to do, we are replacing that ferrous materials with the non-ferrous materials, and by adding some alloying element into those, we can improve, we can enhance the mechanical properties, we can enhance the thermal conductivity, we can improve the ductility properties, we can easily improve by adding some property combinations. So if two good property materials are being combined to each other, what is happening? The output will be more efficient when you compare with the two individuals. So like that, these non-ferrous alloys, we are trying to add some other material into the original material so that the enhancement of the mechanical properties will be very, very good. So alloy systems are again classified either according to the base metal or according to some specific characteristics that a group of alloys have. So depending upon the base material or depending upon some specific characteristics, these alloying elements are being classified. So first one, if you see the copper and its alloys. So first type of non-ferrous material we have here, copper and its alloys. So what is copper and its alloys means? So it is possible possessing a desirable combination of physical properties which have been utilized in quite a variety of applications since antiquity. So generally, unalloyed copper is so soft and ductile that is difficult to machine also. So you have copper which is not alloyed, that means it is not combined with any other material. So before not combining with any other type of alloy, what is happening? This unalloyed copper is very, very soft and has a ductile in nature, and it is very difficult to do machining process. So as it has an almost unlimited capacity to do cold working process only. So during the cold working process only, this type of coppers are being used. So further, it is highly resistant to corrosion in diverse environments, including the ambient atmospheric, seawater, and some industrial chemicals also. So what is the beauty of this copper means? Though it is exposed to different environmental conditions, diverse, that means high or cold climatic conditions, high temperature or cold climatic conditions, or always if it is exposed to seawater, that means you have a lot of salt in the seawater, and also some industrial chemicals are involved, so it can resist the body. The corrosion can be resisted when you use the copper material. So that is what the copper is very, very useful in order to avoid the corrosion for the material. So that is one of the good thing what we have in the copper. Now if you compare the mechanical properties, the corrosion resistance properties of copper may be improved by alloying. Though you have a good values of corrosion resistance, you can still improve by adding some alloying element. So as I said, if two different materials are having two different properties, and if I combine these two again, what is happening? There is an increase in the properties. Similarly, the copper is always before it is having a good corrosion resistance. Now, if you still add some other material, that is some alloy into the copper, which is having a good resistance, then what is happening? It is increasing still more. Suppose if I have some X value of corrosion resistance value. Now, if I add, this is the copper, if you think, it is having X value of corrosion resistance. Now, if I add some alloying element to this, copper plus some magnesium, so what is happening? The corrosion resistance value is increasing with X plus delta X. So you're having a good value. We're increasing, we're enhancing the properties. Like that, if you add some different types of alloys into the base material, the mechanical properties will enhance to do the required material. And also, the most copper alloy cannot be hardened or strengthened by heat treatment process. So generally, the heat treatment means, as I discussed in the previous sessions, if any irregularities are there in the material like this, these irregularities can be altered and make into regular body by heat treatment process. So since copper is very hard, though you heat the material, it cannot be hardened or strengthened during the heat working process. Consequently, even the cold working process also you cannot do. But if you do some alloying element is entered, there is some chance of improving in the mechanical properties for any type of materials. But in this case, the copper, if you are adding some alloying element into the copper, the mechanical properties are being enhanced. And most of the common copper alloys are the braces, for which zinc as a substitutional impurity is a predominant alloying element. So for copper, what you are adding here? Zinc. So this is a substitutional impurity. So because of that addition of these alloys, we are getting the predominant alloying element and enhancing in the mechanical properties. And again, if you see the copper alloys, you have different types of alloys: electrolytic tough, pitch, beryllium copper, cartridge brass, phosphorus bronze, copper nickel, lead yellow brass, tin bronze, aluminium. So depending upon, again, if you increase or if you vary the composition weight percentage between these copper alloys are again classified into different 8 categories. So in this electrolytic tough pitch, what is happening here? Again, it is having some unique number as C11000. And what is the composition here? 0.004. And condition annealing, you are doing some heating process. You are doing heating and you are adding the electrolyte in this, the composition of 0.04. And if you see the tensile strength here, you are getting as 220 megapascals and yield strength is 69 and ductility is 45. So where you can use this type of copper means you can use in electrical wire, rivets, screening, gaskets, pans, nails, like that. Different applications are there. So like that, these copper is being classified into 8 categories depending upon the compositions. So with these compositions, what is happening? There is differences in the mechanical properties. Suppose if you take this copper nickel alloy, you have the code as C71500. And what is the weight percentage of nickel here? 30 weight percentage of nickel. So because of the 30 weight percentage of nickel, this is having 380 tensile strength, 125 yield strength, and 36 of ductility. So where you can use this type of metal means in condensers and heat exchangers, components, salt water piping. So like that, in heat exchangers, you can use this copper nickel type of things. So like that, again, if you go with the casted alloys, aluminium bronze, if you go, so what is the unique number you have? C95-400, and the composition is 4 times of ferrous and 11 aluminium. So again, you're getting tensile strength, a very high value of 586 here, and 241 of yield strength megapascals, and ductility is very less here, 18. So where you can use this type of cast iron means you can use in bearings, gears, worms, bushing valves. So like that, different types of applications. So number of compositions, if you are varying, these mechanical properties vary. So because of these variations in the mechanical properties, the applications are also being varied. So that is one of the non-ferrous about the copper. Now coming to the another non-ferrous, you have aluminium and its alloys. So again, the aluminium and its alloys are categorized by very low density. So since you are having very less dense, what is happening here? The weight is getting reduced. So in the previous ferrous and steels, what is happening? it is having very high dense materials. So because of the high dense materials, what is happening? Weight is increasing. So if you increase the weight, what is happening there? There is chance of reduction in the efficiency. So in order to control these, that's why we are going with the non-ferrous materials. So one of the non-ferrous is aluminum. So this is having very low dense and high electrical and thermal conductivity. So this is very important here. High electric and thermal conductivities are very high. So this should be there for any type of material. So if it is having high thermal conductivity as well as low dense, then its efficiency or the life cycle is very high when you compare with the ferrous materials. So again, many of these alloys are easily formed by virtue of high ductility, and this is evidence that the thin aluminum foil sheet into which the relatively pure material may be rolled. So during the rolling process also, it is very easy for us to do the machining process. And the mechanical strength of aluminum may be enhanced by cold working process. So in the previous cast iron, what we are doing, we are trying to improve the mechanical properties by hot working process in cast iron. But coming to the aluminum and its alloys, by cold working process we can improve the mechanical properties. So that is the word. Depending upon the type of material, the working process also changes. So some may have by adding the alloys by heating, or some can be enhanced by doing the cold working process at very low temperatures. So that is the difference between each individual material. The principle of alloying elements including copper, magnesium, silica, magnesium and zinc. So these are the different types of alloying elements we can involve in the aluminum so that you can enhance the mechanical properties. So what are those? You can combine the copper with aluminum, combine with copper with magnesium, combine the copper with silica, combine the copper with magnesia as well as zinc. So if you do these things with the cold working process, you can enhance the mechanical properties of the aluminum and its alloys. And non-heat treatable alloys consist of a single phase for which an increase in the strength is achieved by solid solution strengthening. So if you do the solid solution, then you can easily increase the strength of the material of the aluminum. And again, each material again is being subclassified into different categories based upon the grades and the unique number. So you have 1100. For this, what is the composition of weight percentage here? You have 0.12 weight percentage of copper. So what type of process you are doing here? You are doing annealing process. That means you are doing heat treatment. So what is the tensile strength here? 90 megapascals, and yield strength is 35 megapascals. Ductility ranges from 35 to 45. So now what type of applications we can use this aluminum means food chemicals, handling and equipment storage, heat exchangers, light reflectors. So these are some of the applications where the weight is very less. In those type of applications, we are going with this type of material. In the same way, if you go with the 5052, again you have magnesia as 2.54% and 0.25 of chromium. And if you see the tensile strength, you are getting about 230 megapascals, yield strength as 195, and ductility ranges with 12 to 18. Now, if you go with what is the applications of this means, you can go with the aircraft fuel, oil line, fuel tanks, appliances, rivets and wires. So like that, see, you have n number of applications. But what type of material you have to select? So this selection of material is very important. Many products are coming nowadays, but selection of material is very important. Why to select that material means you have to have a life cycle, good span of life cycle, and if the efficiency should increase means if you have to select a good material. So how to select the good material means you have to know all these properties. What are the different types of compositions? What are the mechanical properties? If you know all these categories, then it is very easy for us to identify the exact material to that required application. And this is another type of 2090 type of aluminum. So here you have 2.7 weight percentage of copper, 0.25 of magnesium, 2.25 of lithium, and 0.12 of zirconium. So these are all different compositions you have. So based upon these alloying elements, what is happening? There is an increase in the mechanical property. So what is happening? Suddenly it is increasing from 200 to 455. So this is having very good mechanical properties of tensile strength, 455 megapascals. Even the yield strength is also having a 455. and the ductility is very less. It should be there 5. So where you're using this type of 2090 type of grade means in aircraft structures. So aircraft structures and cryogenic tank cage structures. So all these things, very complex structures are being done with this type of 2090, which is having a good alloying element in that. So that is how you have to select those materials to the required applications. So this is about the ferrous and non-ferrous alloys, which can be used in different applications, wide variety of applications, and how are the properties are being varied depending upon the compositions, and how to do the alloying by whether hard cold working process or hot working process. So if you know all these things, then it is very easy to identify the properties. So if you want to increase the mechanical properties, you have to do some alloying. You have to add some alloyings into the base materials, either by hot working or cold working. So if you do this, then it is very easy to enhance the mechanical properties, so that what type of mechanical properties we can achieve? We can achieve the ductility, thermal conductivity, mechanical strength, yield strength, tensile strength. So like that, you have n number of properties. All this can be improved. So once if you improve this, then it is very easy for us to select that material to the required application. And also, identification of the microstructure is very important. So by seeing the type of structure, so how that graphite flakes are being arranged, and how these graphite flakes are being surrounded with the pearlite. So if you see the dark graphite which is surrounded with pearlite, then it is called the grey cassette, since it is looking in the form of grey. Similarly, if you identify any white patches on the microstructure which are surrounded by again the pearlite, then the type of cassette is called the white cassette. So like that, you have different types of irons based upon the microstructure, based upon the composition. So these are all are varying depending upon the composition. So that's why composition is very important. So if you know the composition, at what temperature the microstructure is varying, so that it is very easy to draw the microstructure, draw the phase diagram, as well as to identify what type of material it is. After identifying all those things, then it is very easy for us to do the application. Next, coming to the non-ferrous. Why we are going to the non-ferrous alloying elements means because the irons as well as the steels which are being used in a wide range, but they are also having some drawbacks. Like they are having very high density, less corrosion resistance, less thermal conductivity. So these are some of the drawbacks. So in order to improve, or in order to overcome from these drawbacks, we are trying to get into the non-ferrous alloying elements. So like copper, aluminium, all these things. So if you go with these are having a high thermal conductivity, less density, a good mechanical properties. Also, we can enhance the mechanical properties rather than the original base material. So that's what we have in this session. So if you want to have the references, what are the topics we have discussed today, you can go to the Introduction to Physical Metallurgy by Tata McGraw-Hill, and Essential of Material Science and Engineering, and the other one is Material Science and Metallurgy. The last one is Material Science and Engineering. So all these are some of the references where you can get the information of today's session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.